Welcome back to the City Structures channel. In this video, we shall begin our load modeling series where we embark on defining actions on structures by giving them qualitative and quantitative aspects that we can use for design. We shall define these actions as per the Eurocode's regulations. We shall do this in the general case, but there will be scenarios. We shall consider the nationally defined parameters, the NDPs. Our first action will be the wind load, which will be taken up by Eurocode 1, Part 1.4. There are various ways wind can be modeled depending on the nature of the structure and how we should apply it. In our case, we shall look at modeling the peak velocity pressure. This is the maximum pressure a structure can experience due to wind. It is used to determine the force exerted on a structure, either globally, which means on the whole structure, or locally, which refers to just some components or appendages of the structure. We shall look at how to model this aspect of wind using a simple Excel sheet, the one on screen, and this one is made available for free. You can just download it there's a link in the video description. We shall not be considering any national annexes, rather we shall be using just the general or recommended approach when it comes to determining things like coefficients and non-principal clauses. If you like to see more videos like this where we learn how to design more intentionally, then like and subscribe to the channel and let's learn together. So let's get to it. Of course, the procedure for peak velocity pressure computation has involved a lot of experiments and experiential application, and we cannot go through all of that right now. So what we'll do is basically try to understand the procedure from an intentional design point of view. Now we shall do this in 3 steps. First, we shall consider site and project information. We shall be the fundamental basic wind velocity, the terrain description, and the design life. Then secondly, we shall look at computing the corrected basic wind velocity. Then lastly, we shall now be computing coefficients for dynamic pressure or the kinetic energy of our fluid. So in our case, this is the moving air. These coefficients shall account for variation in wind velocity, which shall give us the mean wind velocity, that is the VM. And we shall also be computing coefficients for accounting for the presence of wind turbulence. Now, the dynamic pressure equation or the peak velocity pressure equation is illustrated in equation 4.8 of the code, so you can just check it out. Now, take note that the peak velocity pressure varies with the reference height. Therefore, we can have a graph showing how wind pressure varies along the height of the structure. This is useful in case where we're dealing with a very large structure. Maybe we want to consider the pressure at different heights, but in our case we shall only consider a specific height above the ground. Later on we shall look at this maybe by using a simple spreadsheet and a graph, so just stick around and we'll see. So we move on to the Excel sheet. We begin with the project site information. First of all, the site location. Now, this is just a geographical naming or description of where the site is. You have to give this so that whoever is checking your work knows exactly where this data or rather this information is going to pinpoint to. The next step, we look at now the fundamental basic wind velocity. Now, this is a nationally determined parameter, and one important thing is you have to make sure the data you're obtaining considers 10 minutes gust of wind. Now, this is what the Eurocode has been modeled for. There can be, of course, from meteorological data, you can find different values based on different wind durations. You can have 3 seconds, 1 minute, 1 hour. So it's upon you to make sure that you're modeling with the right duration of wind. So there are various ways you can convert this. So it's upon you. Just check through the literature and you figure out how to do it. Next up, we have the density of wind. This is also a nationally determined parameter. For my case, I've used the Eurocode national annex, which provides for 1.25 kilograms per cubic meter for the density of air. Now the reference height, now this refers to the height at which the point we want to determine this pressure. So you'll note that in the Euro codes for the description of the height Z, it might not have E because it's just referring to height itself. But for my case, I only want to look at the external wind action. That is why I've added the E, so that refers only to the external wind. Next up, we have the design life. This one is important depending on the type of structure you are set to design. We can have things like billboards, which will have a design life, maybe a shorter one, maybe 25 years. Then we have the typical buildings, 50 years, for example. Maybe for my case, I can try, let's take 25 years. Then we'll notice how this is affecting our modeling of the wind action. Let's go through. Next up, we have the terrain category. Now this determines how wind flows with respect to the nature of the land surface. So there might be obstructions, things of that sort that you'll notice as, for example, if I am to just select category 0, which is sea or coastal area exposed to the open sea. Now, ideally, there will be minimal obstructions from the sea. That's what we're assuming here. And as we go by increasing maybe the value of the terrain category, we realize that the wind action will continue to reduce because there are more obstructions to the wind, therefore providing some resistance and reducing that force. So this terrain category affects these values here: the roughness length, the minimum height, and also perhaps only the Z, what is the minimum height. Now the maximum height, this one is just it's a value which has been determined based on the scope of the Euro codes, especially this part, Eurocode 1, part 1.4. So it considers only a maximum height of 200 meters, so you cannot go beyond that. Rather, you need other guidelines or guides to help you to determine wind action for that. Next up, we move to the basic wind velocity. Now, as we had said, so we are trying to correct, or rather what you'll note is we're trying to correct the fundamental basic wind velocity into just the basic wind velocity. Now this one, to correct it, we have to consider things like the direction factor, the season factor, and also the probability. Now this is where the 25 years comes in. So ideally, Eurocodes is rather its coefficients are modeled for 50 years design life. So if I were to give these 50 years, you'll note that the probability coefficient is 1. So that is what is commonly used, but for our case we want to use 25 years. Now these coefficients, that is direction, season, and probability factor, are the ones used to correct the fundamental basic wind velocity into the basic wind velocity, as you'll see here. So you've moved from 28 meters per second in our case here to 26, so it's been dropped down. Now moving on further, we begin now to model, or rather to compute the coefficients for the dynamic pressure. So as we go down, you notice we have things like terrain factor. Now before I even go there, let's just go down completely to the final peak velocity pressure equation. So you notice here we have one coefficient here, then we have this VM, which I talked about, which is the mean wind velocity. Then the IV, that is the coefficient accounting for wind turbulence. So in order to compute these two, now is where we begin from here. The roughness coefficient given by equation 4.5. So it's computed from these values here. Then moving on, we have the orography factor. Now this one, as you see on the comment side here, the remarks, we have assumed that there is no effect on the wind velocity, that is the orography does not have any effect. You can even change it if you want. There are various ways of computing this orography factor. You can just check them in the annexes. Moving on, we have the roughness coefficient computed from equation 4.4, depending on the limitations in terms of the reference height with respect to the minimum height and the maximum height. Then we move on to the mean wind velocity. So from computing these two coefficients, terrain factor and orography factor, we can now compute the mean wind velocity as 24.36. Moving on, we move to the wind turbulence. Now, of course, this one, just before we go to wind turbulence, you note that the mean wind velocity is dependent on the reference height. So as I had said earlier, we can have a graph showing just the variation with respect to height, but for our case, we'll do that later. Right now, we just want to deal with a specific height. Likewise, the wind turbulence also is affected the same way, depends on the height. So computation, we begin with the turbulence factor, given it as 1, just as per section 4.4. You can check it in the Eurocodes. So here we have equation 4.7, which is now used to determine the wind turbulence with respect to the reference height. So it also depends on the inequalities provided, so it determines which equation to use. Then moving on, now we go to the peak velocity pressure. Now this one combines those coefficients and then adds in that fundamental equation. That fundamental equation is this one from here, 0.5 times density of air times velocity squared. Now this is the dynamic pressure itself. So having done that, you get now the peak velocity pressure at the height given, or rather the specific height. This is how we now compute it just for a specific height. Now in the next video, rather, we might consider using different, or rather varying the height to see maybe as it goes from one point to another in terms of elevation. So we can see how we can model this, and perhaps we can have an Excel sheet for the same. So if you like to see this video and more videos like this, don't hesitate to like and subscribe to the channel, and see you in the next video.